I'm Chris Rowen, and it's a pleasure to talk today about live speech and speech interface in the context of AI. There's really a revolution going on. And my colleagues at ARM and I are eager to talk about what we're doing to push this forward. I represent BabbleLabs, but BabbleLabs is right in the midst of being acquired by Cisco. So all this technology you see here is really becoming part of the Cisco WebEx portfolio. If we think about speech, it really is an important user interface. In fact, it is the ultimate human user interface. You can think of this as an interface that has 7.5 billion users today and has been in development for more than 100,000 years. And in fact, speech is essential to every aspect of society and commerce. It is this rich encoding of words, of text, of identity, of emotion, of location. In fact, it captures much of what makes human culture. But speech communication and speech user interfaces face major limitations despite 140 years of effort. This is, in some ways, one of the original electronics problems, and it's still unsolved in many ways. The limitations come from noise at the source. It comes from conflicting speakers overriding one another. It comes from bandwidth limitations in the communication, channel impairments, that is noise or interruptions or dropouts that occur in communicating that captured speech. Latency is a big issue, especially in two-way conversations because of the lag that causes people to talk over one another. And in audio-only communication, you lose the visual clues that are a secondary but valuable contributor to being able to hold a real conversation. And if you look at what it means to improve speech, there are really two major areas that BabbleLabs has been working on: speech enhancement and speech user interfaces. Speech enhancement is simply the problem of capturing or recovering clean speech of maximum comprehensibility from noisy, reverberant environments and channels. And its applications are pretty broad. Obviously, telephony, but also conference calls and contact centers, video recordings, forensics, where we want to recover what was really happening from body cameras or court reporting or any of these environments. But there are so many places where it's either impossible or exhausting to figure out what's going on in a speech interface. The cases of live speech are the hardest because you have tiny latency budgets. You have to get this done within a few milliseconds or maybe a few tens of milliseconds, but you don't have hundreds of milliseconds. You can't look ahead in the stream to figure out what should have been said. And it very often has to occur at the edge. That is not in the server, but at the edge, because that's where you have the greatest privacy and the least likely impact on latency. And just to give you an example, I invite you to click on this simple before and after for a series of statements, in this case, some commands, to give you an idea of what you'd like to do in very noisy conditions. So click on the first one to hear speech that is sort of in the original, and this one that gives you that same speech after it has been cleaned up using deep neural network-based speech enhancement. So how do people attack this problem? Well, for some time, people have been attacking this problem using signal processing algorithms. And in fact, we recently looked at what was done over the last 40 years. And we looked at the best DSP-based algorithms over the last 40 years and re-implemented them consistently and ran a consistent set of speech enhancement tests on them to compare what kind of improvement was made from the original to the output of these algorithms. And we chose a fairly common metric, that is PESC scores. PESC is an ITU standard for the quality of speech communication. We looked at how much did the speech improve as a result of applying the algorithm. And what we found is that for realistic test suites, there has been, meaningful but modest improvement over the course of the last 40 years in these algorithms. But then just in the last couple of years, as neural networks have been applied to these algorithms, we've seen a dramatic hockey stick in performance improvement. Suddenly, we're able to virtually eliminate the noise, the reverberation from these algorithms. And so we are at the start of a revolution. Now, why is that? I think we can look inside the nature of noise and see how these new algorithms are fundamentally different and more versatile. If you think about noise, you could broadly categorize two classes. There are stationary noises. These are steady in frequency and often reasonably low frequency. So fans, air conditioning, the rumble of equipment often fits this category. And in fact, you can see in this spectrogram, time versus frequency, that this fan has a set of fairly narrow, low frequency bands. And if you click on the icon, you can hear what classic stationary noise looks like. The DSP algorithms tend to be pretty good at this category because these algorithms, by and large, are adaptive filtering algorithms which identify which are the steady frequency bands and work to subtract those out so that the fundamental variability of speech is what differentiates it from the noise. But what happens when you have other kinds of noise? And maybe the worst in some ways is human babble noise, that background rumble made up of speech, so that it has exactly the same frequency characteristics of speech, and it has some of the same variability over time. And you can see in the spectrogram that there's a broad range of frequencies and everything is time varying. And if you click on that, you can hear how different it is. And the classic DSP algorithms have struggled with this kind of speech. But this is the kind of speech that's often most important to get out of a crowd or a street scene or a busy office. And so the ability to handle this broader category of noises, the non-stationary noises, is really what particularly distinguishes the neural network algorithms, because they are learning all the structures of human speech when it's comprehensible versus when it has been reduced to a puree of sounds, as in that babble noise. So within this revolution, there really is a lot of progress being made. And in fact, as you saw in the chart, what we were doing 2 years ago was already a big step forward relative to the historical trend for DSP algorithms. But as we have pushed towards broad-based deployment, we care enormously about not only the effectiveness, how much noise we can remove, but also the efficiency, how well this is going to run on mainstream low-cost platforms at low energy. And so we've recently developed and put into product use two variations of these algorithms. Our full performance algorithm, which is our purple dot here, which improves the noise reduction by another 50% over where we were less than 2 years ago. but reduces the compute load by about 15x. And then a low power version, which is still better than the old 2018 version, but is 100x less compute than where we were just 2 years ago. And I think this is symptomatic of what we see more broadly in these speech AI problems, which is that there's an enormous amount of leverage that you get from advanced training using sophisticated data sets and in tuning both the algorithms and the implementations to be able to deliver remarkable experiences really in very low power and very low compute cost. You can get an idea of the effectiveness looking at these 6 pairs, the original sound, and then after our clear edge speech enhancement is applied. I invite you to click on a few of them. Maybe the baby crying and the baby sound eliminated, the dog barking. In an era of work from home, I think many of us are so eager to present a professional face, even when we're working in rather non-professional environments. So eliminating the typing and the baby and the street noise and the dogs are really important goals. So play around with that. Look at before and after for a couple of cases. We can go on and say something about how speech user interfaces are transformed by this same attention to differentiating the substance of speech, the important part of speech, from everything else around it. That this problem of building a speech user interface is really important because not every environment is a quiet living room. Now, we know the great success of the the Amazon Echoes of the world that happen when you have really clean environments. But you take that onto the street or into the train or into a factory floor or out into a crisis situation, you do not have control over the environment. And so you have to make speech user interface work in all those environments. And in fact, speech user interfaces are particularly important when the hands and the eyes are unavailable for conventional buttons and screens. So we're particularly interested in those chaotic, noisy, hands-free environments, places like healthcare and public safety, on the street, shopping environments, where you don't want everybody touching the same touchpad. And you often, in those environments, also often have mobility. So you want tiny compute budgets, tiny memory allocations, low network bandwidth budgets. And so we want to build very robust user interfaces using neural networks that meet several dimensions of robustness. Robustness means always available, so not dependent on the network being up, completely private, so they're not always listening and sending everything you say to the cloud, that works under worst case noise conditions, that is speaker independent. So even people with significant variations in accents experience the same high quality, robust, reliable recognition. And something which supports significant grammars so that you don't need speaker training, you need only have the idea and the vocabulary of the user interface is sufficiently general to satisfy people's need to just use the intuitive command to do something. So how do we go about this? Well, there's an inherent problem in the existing systems. Today, many user interfaces rely on the same automatic speech recognition, ASR systems, that are used generally for transcription. But what happens in most of those systems is that there's a significant dependency on the noise level. So I'm just taking one of the most popular and successful speech user interfaces, in this case, IBM Watson. It's a great ASR engine. I could get very similar results if I looked at Google or Microsoft Cortana. They're all great ASR transcription engines. But in the context of command recognition, they suffer. So if you just listen to what happens under clean conditions, that is at high signal to noise ratio, you can see on the spectrogram and you can hear that the commands are quite clear. And in fact, IBM Watson does a great job of picking them up. If you go to higher and higher noise, that is worse and worse signal to noise ratio, you can see both visually how the structure of speech is lost in this muddle of noise. You can hear it, and you can see in the accuracy of the speech recognition that by the time you get to 0 dB, pretty much you're lost. There is no ability for these systems to extract out any useful information. But why is that? So what's happening that causes that problem in recognition in the presence of noise? When things are quiet, you've got a relatively clean speech coming in. You may go through a noise filter. You go into an acoustic model, which takes that waveform and maps it to a string of phonemes. For example, if somebody says power on, you get power on. Then a language model for English, for example, will map from the string of phonemes to the most probable string of words, power and on. And that text stream, that word stream, goes to a natural language application, which is looking to find the interesting statements from its grammar. So it knows what power on and power off and other things may be. If there's some noise, however, we might have confused the acoustic model so that it gets power in. And then the language model gets the wrong thing. And the natural language application doesn't know what to do with it because power in isn't part of its grammar. And so it ignores it or it does the wrong thing. A better way of approaching this problem is a more unified model in which the noise filtering, the acoustic model, the language model, and the natural language application, the grammar matchup, is all done together. And by doing that, we overcome this problem of ambiguity. And in fact, the network is only looking for the commands of interest. And if power in isn't one of those commands, then it will never get that wrong. And it's much more likely to say, well, the closest thing to power in is power on in the context of the grammar that we have here. And so unified models can handle the ambiguity of noise in a significantly smarter way. So when we build user interface using neural network for command set recognition, we can do a better job. And in fact, here is our clear command technology, which for exactly that same audio does a significantly better job than a large cloud-based ASR system, which may be 100 to 1,000x bigger and take vastly more compute than something which is targeting a specific vocabulary. Of course, there's always a point where there's so much noise, even a very noise-robust system starts to make a few mistakes. But the knee of the curve is much further out, at much higher noise before it really becomes problematic. If we look at this down in more of the guts, we find that this unified model, it really implements a whole family of recognizers. in this particular case, we're doing spectral domain processing. So we really are doing a kind of image processing on the time frequency spectrogram. And we're using a set of techniques derived from residual networks with separable convolutions and one-by-one convolutions. But with it, we can typically build fairly sophisticated recognizers with tens to as much as 100 different commands or intents, and do it in a relatively small footprint. So depending on the demands of the vocabulary and the level of noise immunity that's required, we typically range from 50,000 to 250,000 parameters, all 8-bit, and require, depending again on the scale of that network, 20 to 100 million multiplies per second, something that can be done in almost any CPU, DSP, microcontroller. There are a wide range of choices. And we've done optimizations that mean the working memory footprint is really small, like 128 kilobytes of memory. Here's an example from one 30-command set where we looked at the accuracy, in this case F1 score, as a function of signal-to-noise ratio. As you'd expect, at high signal-to-noise ratio, under quiet conditions, it's very accurate, well above 95%, even for the smallest models. But as the noise level increases, the signal-to-noise ratio gets worse, you see this gradual decline. Certainly much better than those ASR-based systems, which may be only 50 or 60% accurate under high noise conditions, but some dependency on the model size. So here's about 110,000 parameters, 136,000, 166, 199,000 parameters. You can see that for this particular model, it really pays to get above 130,000 parameters. But then we're getting better than 95% accuracy at 0 dB, where in the ASR case, it was pretty much completely gone. Here, it's pretty much completely correct. And so what we've really got is a technique here in user interface design that allows us to be very robust and have quite small footprint. And in general, as we look at these neural network applications, we see that there are a wide range of choices of compute platform, with some of the classic trade-offs at work. For the greatest flexibility to handle not only a very wide variety of neural network problems, but any other problem, clearly you can go to general purpose CPUs, and x86s and ARM Cortex-A kind of all fit that category. And in fact, they generally are even more efficient when you add in their respective vector and instruction set extensions like AVX2 and Neon. Microcontrollers are pretty good as well. They don't have the same multiply efficiency, but they otherwise are very lean machines so that you can have quite general flexible solutions at higher and higher efficiency. But as you push towards really low power operation or really high throughput per dollar and throughput per watt, then you see the domain for DSPs and GPUs. And ultimately, we see a significant role for neural network accelerators. You give up something in flexibility. That neural network accelerator won't be good for doing other computing tasks. You won't use it effectively, at least, to run general purpose control code. But in the context of running these compute intensive convolutions, it'll be great. And so you can get to very high efficiencies. In fact, we've been working with ARM directly on evaluating how neural network acceleration works on general purpose microcontrollers and in specialized accelerated engines. And so I'm pleased to pass the ball to Richard Burton, who's going to talk about the work that we've done together on speech user interface for these kinds of engines. Go ahead, Richard.
Thanks so much, Chris. So my name is Richard and I work in Arm's machine learning ecosystem team. And recently we've had the great pleasure to work with Chris and BabbleLabs to try and evaluate some of the ML workloads that he's just talked about on some of our latest IP and software to see how we could help accelerate and get even greater performance from them. So as we've seen, running non-trivial ML models on embedded devices is very much something already being done today. There is also no doubt that the number of devices running ML at the edge is only going to keep growing. This is something we at Arm are super excited about and are really keen to help nurture. Now, squeezing all the performance possible out of a tiny embedded device is essential if you want to run any serious kind of ML workload, like speech recognition, on such a compute-restricted device. So as a result, at Arm, we've been working hard to really turbocharge the ML inference on the Cortex-M devices. One way we're doing this is with a software library called CMSIS-NN. So CMSIS-NN is an open source library of optimized compute kernels for Cortex-M devices. And these optimized kernels aim to accelerate the key ML operators found in modern neural networks. It also helps to reduce memory footprint with clever data reuse. It's completely open source, so you can check the code out on the link in the slides, and we welcome contributions to make it even better. One thing that's recently been worked on is to have much tighter integration with TensorFlow Lite Micro. So as a result, it's now easier than ever to take your trained quantized model, deploy it on a Cortex-M device, and have it accelerated for you. Testing this with one of BabbleLabs' Command UI models, we profiled the kind of speed up we could get with CMSIS-NN. So at the bottom of the graph on this slide, we started by having their model run on TensorFlow's reference kernels. And we can see that by using CMSIS-NN on a Cortex-M7, we were able to achieve a near 4 times improvement to inference speeds. Afterwards, we tested on our latest Cortex-M device, the M55, and we saw the kind of boost to ML workloads the M55 provides. So using CMSIS-NN, we more than double the performance compared to running on an M7. So we've done our best to get as much as possible out of our microcontrollers, and for a lot of use cases, this will be more than enough to satisfy your tiny ML needs. But what if it simply isn't enough, and for this kind of model that you want to run? Maybe your model requires too much compute and your application is left waiting too long for an inference to complete. However, where you're deploying it, energy and area might still be very important to you. Well, this is where our latest embedded product, the Ethos U55, comes in. Ethos U55 is what we believe is the first ever micro MPU. This means it's a neural processing unit that is targeted primarily at the embedded space. So you pair Ethos U with any compatible Cortex-M device, and by using TensorFlow Lite Micro, your application will offload neural network inference to the Ethos U for acceleration. One of the nice things about it is the application code for deploying on Cortex-M or Ethos U is virtually identical. So it's super simple. One thing we do require is that you first optimize your model with our offline optimizer called Vela. Vela will inspect your TF-Lite model, look to see where it can optimize the model by fusing, reordering, or removing operators ready for Ethos U. And this is again something we've open sourced. So using the same code as before, we deployed the BabbleLabs model on the U55, and the charts in this slide show the kind of results we got. This time we used Cortex-M55 with CMSIS-NN as a base, and we see nearly 14x speedups of the smallest Ethos U configurations, going up to nearly 80 times speedup at the higher end. So these big speedups you can achieve with U55 not only allow you to run more compute-intensive networks where latency is important, but also potentially gives you room to run multiple networks on one device, one after the other, opening up new potential use cases. Of course, inference speeds don't tell you everything. So by utilizing an Ethos U, we can achieve large energy reductions for ML workloads, like speech recognition, compared to using just a Cortex-M, if you were to compare just using Cortex-M. More than 90% in some cases when comparing to older M7 devices. We also wanted to see how efficient the Ethos U is if you throw more compute units at it. And using a similar model to the BabbleLabs one, we evaluated the energy use per inference for different configurations of U55. So on the graph here, we can see that the Ethos U architecture can utilize these additional MACs to efficiently run inferences. By working with BabbleLabs, it's helped us to demonstrate the kind of performance gains you can expect with real-world networks and why M55 and Ethos U55 are such great choices for running ML workloads at the edge. I'll now hand it back to Chris for some closing remarks.
What we hope that you've seen today is that, first of all, speech is really an ideal target for AI. It's a very complex, nuanced representation of many kinds of information. that are otherwise very hard to extract and analyze and clean up. But neural networks, because of they can be trained on massive amounts of speech, make it possible. Yet, the problem is computationally tractable. You can run it across a very wide range of platforms. And in fact, with things like the Ethos, you can now run it even in very low energy environments. Second, we are just at the beginning of a revolution. We expect that this pace of speech innovation using AI that we've seen in the last couple of years is going to accelerate, persist for some years to come. We have seen very little yet of what is going to be possible. And I think that we're going to see a diversity of new algorithms, especially at the edge, that can handle the real-time demands, the mobility demands, the robustness demands that we expect from ubiquitous devices, whether they're in our phones or they're wearables, and where we really care a great deal, not only about how accurately they perform, but how mobile, how energy efficient they are. So buckle up. I think we're entering a really exciting time for speech AI. Thank you.